Ready for next talk? Okay, the next talk, the speaker, c'est professeur Gael Meignez de l'Université de Marseille. Professor Meignez is going to talk about towards the ultimate generalization of Novikov's closed-leaf theorem. Merci.
Thank you. So,
Yes. Say something.
did it work?
Tá funcionando o microfone dele?
Uh-huh. Ah.
Não, ça marche.
Okay. So, very first talk to give
Eu acho que eles vêm por
I was just beginning the and he that explained that
Rather luckily, I didn't really realize what was IHES, nor who was in the room.
Oui.
Sorry. So,
Ah, better? Characteristic of what Raman told us yesterday in Paul's caring and attention and confidence towards young people. Then I had several opportunities to work on subjects in which Paul had made before some really groundbreaking advances. I'm thinking of flows without periodic orbits on three manifolds, or also in high dimensions, foliations of codimension 1 without compact orbit, without compact leaf. And this is, of course, also the case of this subject, where the history has essentially three steps. So Novikov in 1965, he proved that, well, in particular, that every foliation of codimension 1 on S3 contains a rep component. A rep component, as we know, is like this. It's a foliation of the solid torus. The boundary is a leaf, and the other leaves are like this and turn around it. And there was this fantastic paper by Dennis Sullivan in '76, and well, so Novikov's proof has the proof of Novikov's theorem has two steps. Because of the ambient topology, you are able to prove that somewhere in the foliation there is a vanishing cycle, which is in this dimension a circle in a leaf that is not homotopic to 0 in this leaf, but where you can push it continuously to neighboring leaves where it becomes homotopic to 0. And Sullivan had a homological approach, valuable in all dimensions. And he gave some elements of arguments with deep view on what he called homological proof and generalization of Novikov's theorem. And then the third step is Alcalde Cuesta Hector and Schweitzer. And probably approximately 1995 to present. Because when I became an assistant professor in Lyon in 1995, if I'm correct, Paul and Fernando were there, and Hector's office was next to mine, and they were there speaking of this beautiful subject already. As Gilbert explained us yesterday, they have made a generalization of Novikov's closed-leaf theorem in higher dimensions. I mean, of the second part of Novikov's closed-leaf theorem, going from a vanishing cycle of some nature to some kind of generalized rep component. So what I would like to speak to you about is a kind of analog to their theorem, which is in any dimension, and which is somehow discrete. Instead of a continuous family of cycles, you take a convergence sequence of cycles. And also, a second aspect is that it will be not really about cycles. I mean, somehow it's more basic, about point sets. So let's consider, since it's discrete, there is no use in foliations. It works for laminations. So our domain will be a manifold of dimension p+1, and on this manifold, a lamination of codimension 1, which will be a compact, the support of the lamination, and say transversely oriented. Then you have plaques. I will take the word plaques in very general sense. What is a plaque? It's a subset in a single leaf. Une seule feuille a suffi. A subset in a single leaf, which is compact for the manifold topology of the leaf. That's all. And when you have a plaque, you can consider its topological boundary in the leaf. And it's also a plaque. Now the theorem is as follows. Assume, so you take a sequence of plaques. Assume that the boundaries converge. Well, we're speaking of compact subsets of M. So we consider the Hausdorff topology and the compact subsets of M. So converge Hausdorff in M to some plaque Z, which I think has a kind of cycle. Then I consider the accumulation points of the sequence of compact sets pk. And it can be a plaque. This is the trivial case, something like a vanishing cycle, which is already homotopic or homological to zero in its leaf. Or, well, so the definition will be what is a Reb lamination? A Reb lamination has a lamination with a unique compact leaf. So first of all, at least two leaves. A unique compact leaf L0, and its holonomy is infinite cyclic, and all the other leaves are proper in the foliator's sense. It means that it does not accumulate on itself. And in fact, the closure is L cup L0. So it accumulates nothing but the compact leaf. There is a little something, it's not exactly correct like this. Yes, because or it's not finished, because as Gilbert told us yesterday, there are some kind of strange other cases, like about foliations which are more or less like irrational linear foliation on the two torus or things like that. There is another case which is uninteresting, in fact, and which I call Dangerois lamination. definition. So maybe for Reb lamination, I should insist on some examples. So of course, the classical Reb component, but you can also take just two leaves, the boundary leaves, the boundary leaf, and one interior leaf. This is a Reb lamination. Or you can, of course, play to take Cantor set of internal leaves and the boundary leaf. Or the same with a generalized Reb component in the sense of Alcalde Cuesta, Hector Schweitzer, that Gilbert explained to us yesterday. All these are Reb lamination. So, now a Dangerois lamination, on which I don't want to insist too much. There exists, so first of all leaves have two ends, are non-compact. Two ends and no holonomy. And there is a unique minimal set which may be equal to D or not. And the two examples that we should think about are linear foliation on T2, of course irrational, and the Dangerois example. Here D equals D naught, and there D is not equal to D naught. But, so it's because you see, since the leaves have two ends, you can take two hypersurfaces very distant in the leaf that bound a very large part of the leaf, and you can play to make these guys in M converge rather stupidly to opaque, and so that makes obviously some kind of vanishing cycle in this sense. Maybe it should be called a point set vanishing cycle. So, and my theorem here is not quite correct because there is a little something. It's correct. I've introduced transverse orientation. It's correct if I assume that the boundaries of the plaques are converging from above to Z, which is not difficult after extracting subsequence. And then I guess that it's correct. Of course, you can give more precision on the conclusions. Okay, so what I would like to first of all, to give some corollaries and some applications and explain the relations with the theorem of Alcalde Cuesta, Hector Schweitzer. And then I'll try to give some elements of the argument for this theorem. such a point formula, you can give a homological, more or less equivalent form. So you've understood the philosophy. The philosophy is that, just like here, you have these large domains, which are plaques in the large domains in leaves, but the boundaries are not large. The boundaries converge very nicely, bravely to a plaque, something compact in a limit leaf. But these guys do not converge to something compact in a limit leaf in general, and the accumulation point of all those guys is a red lamination, or eventually a danger lamination. So, the homological, you can get from there very easily a homological form, much more like we're used to. Well, with objects like chains, it's really of no importance. You can take currents, lamination currents. CK a lamination P current in the sense of Sullivan. If you're not comfortable with it, just think to singular chains, which is plaque lamination P current in the sense that the support is a plaque, and you assume that the boundaries converge weakly from above to some plaque lamination P-1 current. And you also have to assume that the boundary, that the supports well, they are good. So the limb of the supports is a plaque. So you assume that Z is not a boundary in limit leaf. Then, same conclusion, the limit SIP of the supports of CK is a Reb or a Danjois lamination. And so, once you have such a discrete version, you can easily get the continuous version, exactly the one of Alcalde Cuesta, Hector Schweitzer. But you don't need any regularity with respect to nothing, and any continuity with respect to nothing. You have just the same with a continuous parameter. So consider a foliation of codimension 1, of course, and say that it is of class C2 with holonomy. because by Saxteder's theorem, you rule out the Dinjois things. So it's simpler. And consider an embedding of the interval in M transverse to F. Consider for every T positive a P current in the leaf through T, and assume that the boundaries converge for T goes to 0 vers Z, P minus 1 current in R0, wiki, and assume that Z is not a boundary. Then the limit sup of the supports of CT for T 0 is a generalized Reb component in the sense that Gilbert explained to us yesterday. So the advantage of this little version is that, so it's really easy. You just consider all the sequences going to 0, and for each of them, the theorem tells you that you have a Reb lamination, and you just have to verify that all these guys fill a genuine generalized Reb component. So the interest of this version, I think, is that you really nothing as hypothesis of continuity or regularity. Well, and I would like to give corollaries, applications, which are actually corollaries of the theorem of Alcalde Cuesta, Hector Schweitzer. And I would like to insist on the existence of these corollaries. Since after all, for Novikov theorem, you don't know only that a vanishing cycle implies a Reb component. You also know that in some interesting circumstances, you can prove the existence of a vanishing cycle. So, here, of course, it is much more delicate. Essentially, the reason is that if you want to do things, what you get rather easily is the existence of vanishing cycles of dimension 1. And what you need to apply this is the existence of vanishing cycles of codimension 1 in the leaves. And so it's completely different, of course. Actually, it is known that the very naive things that one could hope do not work, and it is known by Paul's work. So recall Paul's result in 1995 that every manifold of dimension at least 4, whose Euler characteristic is 0, admits a codimension 1 foliation of class C1 without compact leaf. And no, it was, at this period, it could be thought that there was a differentiability thing, but in fact not. I could prove later. that there exists even a foliation of class C infinite, which is minimal, all leaves dead. So really, the naive generalization, for example, an S5, so the naive generalization of Novikov theorem in this very uniquely topological context cannot work in class C infinite. So you can think of maybe there are some generalization for foliations with some tangential structures like foliations with a tangential symplectic structure like the ones that Yoshi constructed, or things like that. But actually, you can say something for transversely analytic foliations. So from now, I'm thinking of a transversely analytic codimension 1 foliation on a closed manifold of any dimension. And then you can say some things. So here is the general fact that you can get. You would dream of something like the pi, some homotopy groups of some homology groups of the leaves would inject into the ones of the manifolds or things like that. You don't quite have this, but you have something. Namely, one has the following. Consider the universal cover. So in the universal cover, since F is transversely analytic, you know that the leaves upstairs are properly embedded hypersurfaces. So you can consider the homology of M tilde with respect of a leaf upstairs, and that is and in dimension P. And the theorem, if one of them is non-zero, then F downstairs contains a generalized drape component. And the reason why, very vaguely, the reason why you can do something like this is, of course, you're dreaming of doing something like Heffliger's lemma, which is the first part of the proof of Novikov's theorem, but in high dimensions, it's a mess because you don't have, because the foliation restricted to a compression disk, to a high dimensional kind of compression disk, is anything. It still has a lot of dynamics. But once you are upstairs, then consider your L tilde, and an element of this HP will be, of this relative HP will be a hypersurface with boundary on H tilde, and when you restrict the foliation F tilde here, it's a singular foliation with generically Morse-like singularities, but all leaves are closed. So you can make this argument. It's not so easy, but you can make this argument of looking for every leaf if it is or is not for every leaf of the restriction to the hypersurface, if it is or if it is not null homological in the leaf, and see what happens. And at some moment it stops to be true. And it's not obvious because you are not downstairs. You have to project things downstairs, and it is not injective. You have to work, but you can get this. And so this has, let me give two very simple applications. Assume, which are completely immediate from this theorem. Assume that that M is aspherical in dimension p minus 1. For example, hyperbolic manifold of high dimensions. If for some leaf downstairs, the homotopy of the leaf, the p minus 1 homotopy of the leaf, is non-zero in the homology of the manifold, then your function contains a generalized red component. No, sorry. Here it is. The leaf also, of course. So it says constraints for so under this condition of sphericity on the manifold, and for a real analytic function, or at least transversely analytic, you have some constraints. If it is rebless, then you have some constraints on the topology of the leaves. Every hypersphere in a leaf has to bound. It really says something. And here is another one. Yes. Assume that the pi1 of M has more than one end. Either two ends or a counter set of ends. Then, so take such a foliation, real analytic foliation. Either F has a generalized red component, or F is a vibration on the circle. So in fact, M does not have infinitely many ends. But for infinitely many ends, maybe this corollary is just empty, because I don't know, maybe people know here, but I could not find out if there can exist any real analytic foliation on a manifold whose pi1 has infinitely many ends. Whose pi1 what? Has infinitely many ends. Closed manifold whose pi1 has infinitely many ends. Can there exist real analytic codimension 1 foliation? I'm not sure. I would say no. Well, this theorem says that it has to have a red component, a generalized red component, but maybe there is not. But at least it has some constant for manifold with two ends. take a manifold whose pi1 is Z, then this says that any analytic foliation on it is either a vibration to the circle or has a generalized red component. This is all that I could get out of these generalizations of Novikov's theorem. Very few time for giving you ideas of proof. I would like rather to give a comment on the proof of the main theorem, the discrete theorem. It is extremely elementary and not easy. You remember there is this very nice argument of Heffliger to show that in codimension 1, this is a very codimension 1 phenomenon, the limit of compact leaf is a compact leaf. He had this beautiful, simple argument considering the homology of the generated by the leaves. And so, no, you are considering people like this. Some huge domains in leaves with a small boundary. So the philosophy is that this is almost a compact leaf. There is still something here, but it's almost a compact leaf. So you take Heffliger's argument and you say, okay, does it remain something? Does it still say something for this situation? We don't have quite a compact leaf, but almost. And yes, it tells you, you can get a little something about the limit set by mimicking Heffliger's argument. And then you work with very elementary arguments, the ones that everybody who works in foliation learns in the first month of his PhD. Holonomy, saturated subsets. Maybe you can go to octopus decompositions and things like that. And progressively you can prove that there is in the limit set, that the limit set contains a minimal subset of the foliation, that actually the limit set is saturated, that is, it contains all the leaf LZ containing the cycle. Then you can, that there is very few holonomy for the leaves in the limit set, just a little on the compact leaf, that on the limit leaf, that the limit leaf is at least upper semi-proper, and then you can prove that the limit leaf is compact. And this is the first part. And then you continue, well, but it's not satisfying because it's a rather complicated way to add little data about this limit set until you arrive at a Rabe lamination. So I was dreaming of a kind of more better argument, a la Sullivan probably, because what you are doing actually is proving that the set of plaques has some kind of boundary at infinity, of ideal boundary made of RABE components contained in the lamination. And maybe there is something conceptual, but I cannot do it right now. Thank you very much. And happy birthday, parabéns, Paul.
Oh, thank you. Do we have questions?
First of all, thank you for this fascinating and remarkable lecture, Gael. I've thought a lot about this over the years, and there's so many interesting new ideas that you have presented, so that's the first thing I wanted to say. But I also wanted to make a couple of historical comments about this problem. The problem of existence of RABE components is a very thorny problem, and it has been very difficult. I'll just start out with RABE's original paper, because the paper was written in Russian in '64 and in English translation in '65. And around '72, I received a request from Centralblatt to write a review of it.
You mean Novikov's paper?
I'm sorry, of course, Novikov's, of course. I'm talking about Novikov's paper, thank you. But anyway, Novikov's paper had waited for essentially 8 years for someone to write a review. So how could that be explained? Well, actually, when I was reading through the paper, it was very difficult to follow the details in the case when the vanishing cycle is not embedded, but has self-intersections, double points. And actually, I couldn't understand that. But then a little later, actually a little before that, Hefliger had given a Bourbaki seminar in which he made it perfectly clear. So that's the first thing to say. The second thing is that we, in our work, thought we had arrived at a complete argument. And in fact, I told that to Larry Conlon, and in his book on foliation, he mentions that, and it wasn't correct. We had made a mistake. And even beyond that, I had another approach over the last 2 or 3 years, and only 2 weeks ago, I discovered that there was a gap in that approach. So it's a very thorny problem, and so it's really wonderful to see that you have been able to do that. So congratulations.
Thank you. Thank you. About any more questions or remarks or comments?
Sorry? Because you have this compact set in a leaf, so it means, so if you have a sequence of compact sets in leaves, you have a kind, well, it's okay. You have a compact set in a leaf, and this is Z in its leaf, and you are and the boundaries ZK, say, they are in leaves, and they Hausdorff converge to it. So you can take an I bundle around Z, a small neighborhood. Of course, it's not saturated. And, but you know that after some time, all the ZKs are here. So it's clear that this has two components, plus and minus, and from above means that ZK is contained in the plus part.
So you're looking at an embedded. You're looking at an embedded neighborhood of the compact set in a leaf.
Yeah. And you don't need, of course, that Z be without holonomy. Yes. Yes, sorry. From above means from one side, from the positive side.
Can I ask?
Yes, please. Now we can hear you.
Okay. So my first question is the vanishing cycle you defined, is it different from averaging sequences of plant, or I couldn't read very well on the blackboard.
Excuse me, I did, and reciprocally, I couldn't hear very well the question.
Oh.
Cut my.
No, I have one question and one comment. The question is, I had the feeling that what you use is an averaging sequence of plants. Do you add something, some more condition to plant's definition, or is it just the same?
There are some, yes, there is using plant in the analysis of what happens in the case of the Dangerois lamination. If you really want to get the Dangerois lamination, there is a moment where you use some plant arguments.
Okay.
Because you need to prove that there is a transverse invariant measure.
Okay, the sound is very bad. But okay, and I have just a comment. If, as I understood, you said that when your vanishing cycle is continuous, then it converges to a generalized wave component. In any case, did you say this?
Sorry, once again, I didn't hear the question extremely well.
Can you repeat, please?
Okay, I repeat. I make a comment, and this is the question. There exist vanishing cycles in the sense I explained yesterday. So they are vanishing cycles in your sense, I guess, in any case, such that the support is not a generalized wave component in the sense I said yesterday. It is something like your wave laminations. So my question is this coherent with your theorem or not?
Did you get it, Paul? I'm sorry, Gilbert. The sound is really not very good. Did you get Paul's?
He was saying
Gilbert's
that
question?
your result coherent with what he was saying yesterday, and especially, I think, the Rabe lamination, and I suspect he meant also the Dangerois lamination.
There is a little difference between the discrete case and the continuous case, of course you. In the discrete case, you can do really anything you want with the extremities, and so there is my Dangerois case is not exactly the same as what you said yesterday. There are some subtle differences because of discrete case and continuous case. But I can tell you, we can discuss this, and I will be very interested to discuss this with you maybe during the conference.
Okay, thank you.
Okay, thank you very much for your questions. Do we have more questions or comments? No? Well, let's thank the speaker again. Now we stop for lunch and we come back at what?